We're going to use now the definitions of aromatic compound, anti-aromatic, and non-aromatic to solve some problems. Here we need to remember those aromatic compounds will be fully conjugated, cyclic planar. Fully conjugated, remember we need to be alternated double single bonds, or all of the carbons, say in this system, all of the carbons are sp2 hybridized. This is fully conjugated. You can do resonance here. Another example is that, but they need to be fully conjugated, cyclic, all of my electrons, planar, and have 4n plus 2 electrons. This actually has 4n. So that will be an example. It's different because this is 4n plus 2. That will be aromatic. So here, I'm going to change that for the anion because that way is another example of an aromatic compound. So we'll be doing that. For if you have 4n pi electrons, n is conjugated cyclic planar, then it will be anti-aromatic. We also learned in previous video that aromatic compounds will have a resonance energy, and that we can calculate that. And that compares the stability, for example, of a fully conjugated system to something that is not conjugated. We did that calculation of resonance energy. You can find that in another video. Okay, and that is about stabilization. Now, let's use that in the following system. Say that we've been asked a question about to determine whether or not the following compound is aromatic, anti-aromatic, or non-aromatic. So let's draw the compound. Why would be that? How do we classify that, in other words? So in this system, in this structure, if we just count the number of pi electrons here, we have 3 double bonds. So 3 pi bonds, so meaning that we have 6 pi electrons. However, the electrons are not all in a cyclic structure, so not a cyclic system. And because of that, we are already not in that rule. So cannot be considered aromatic or not, or anti-aromatic. Is not everything in a cyclic structure. So it's simply non-aromatic, that example. So it's not a continuous. To be fully conjugated, you need to have a continuous system of p orbitals that can overlap. That's the case here and here. That is also, not everything is in a cycle. So yes, there is conjugation here, but it's not this. They are not part of a cyclic structure. So it's non-aromatic. Okay, so let's do another example. If I had the following, let's say I'm using my examples here in this page. So let's see, will this cation be aromatic? So if you analyze the structure, that is a cation actually at an allylic position with respect to the double bond. So everything here is sp2 hybridized, all of the carbons. And so we have a continuous system of p orbitals that overlap. So it is conjugated, fully conjugated. It is cyclic. It is planar. And we have 2 pi electrons. And that actually meets Hickel rule for n equal 0. So n equals 0 is that. So that compound is aromatic. Let's do another example. Okay. Here I have. Well, if we did this, we already mentioned that here, this compound is conjugated. So all of the carbon atoms here are sp2 hybridized, meaning you have a continuous orbitals, p orbitals that can overlap. So fully conjugated, it is cyclic. All of the pi electrons are in a cyclic structure, and it is planar, so it is aromatic. Same as benzene. Now let's draw another compound here. This is structure. Now here you have a cation. This cation, we can do resonance. So this is structure, let me just, I'm gonna draw on top of that to make it darker. Okay. So now we can do resonance here. This is adjacent to a double bond, so it is allylic, and we can do resonance here, right? So we could, in the resonance structure, will be this. And you could also move these electrons over here and do another resonance structure in which you're going to have the positive charge here. So you have conjugation, but notice that there is a carbon here that is sp3 hybridized. So that interrupts the conjugation. You need to have a continuous system of p orbitals. So it is not fully conjugated. And also it's non-planar. That is sp3 carbon. Remember, geometry here is tetrahedral. So the presence of that sp3 carbon prevents that the system is fully conjugated. So in that case, so we say doesn't meet the first rule, so it's not fully conjugated, cyclic planar, so it is non-aromatic. Okay, so despite of the number of electrons, we don't do that. So let's do another example here. One more, and here I have, see how good I'm that drawing. Okay, double bond, double bond, double bond, and here I have a pair of electrons. So that is an anion. And so in here we have this a cycle with 7 carbon, but I have 8 pi electrons. So 2, 4, 6, 8. The system is conjugated. All of the carbons are sp2. The carbons are sp2 hybridized, so have a continuous system of pi p orbitals that are parallel. And now, but here, notice that we have 8 pi electrons. So that compound, having 8 pi electrons, does not comply with Hicke rule, so that will be anti-aromatic. So we will do more examples on that, applying the concept. So remember that conjugated, fully conjugated means all of it. You have to have a extended system where everything you have the overlap of p orbitals. So you can see alternating double bond charge, for example, or alternating double bonds to have that system.